Welcome to The Explainer. Look, if you want to build autonomous AI agents, you absolutely have to understand the underlying architecture. It's like building a house, right? Think of Python as your raw building blocks for constructing these intelligent systems. It's the essential foundation you need to master before you can even think about deploying cutting-edge language models to solve real-world problems.
So, why Python for data science and AI? I mean, why has it become this ultimate platform-independent language that everyone is talking about? Well, first off, it boasts a massive, super active community. That means you have access to countless solutions and forums, which makes the learning curve so much smoother. Plus, its syntax is incredibly readable, and it comes packed with a seriously rich collection of powerful data science libraries.
Here's our roadmap for today. First, the Python AI Foundation. Then, logic and decision-making. Third, functions, modules, and packages. Next up, writing clean, Pythonic code. And finally, powering AI with NumPy.
Let's dive right into Section 1, the Python AI Foundation.
Okay, so our essential workspace for this journey is JupyterLab. Setting it up is actually really straightforward. First, you're going to want to search for and download the Anaconda distribution. Just run the installer and make sure to select the Just Me option. Once that's all done, launch the Anaconda Navigator, and from there you just open JupyterLab. It'll launch directly in your web browser, giving you this awesome integrated environment where you can write, execute, and document your Python code all in one single place.
When you hear variable, just think of a container. In our AI projects, these little containers will soon be holding things like our LLM prompts or API keys. And honestly, the beauty of Python is its intuitive ease of use here. You don't need to explicitly declare the exact type of data a variable holds, like you have to do in some other clunkier languages. You literally just give it a name, assign it a value, and boom, you're ready to start coding.
So these are the core data types acting as the raw materials inside those variable containers. We've got integers for your whole numbers, floats for numbers with decimals, strings for text characters, booleans to represent simple true or false values, and none for variables that, well, currently have no value at all. Getting a quick refresher on these basically gives you a powerful toolbox to tackle almost any programming problem as we build out our agents.
Moving right along to Section 2, Logic and Decision-Making.
Let's look at conditional statements. Picture this. You're coming home from work. If you arrive on time, you decide to cook dinner. But if you're late, you just order food instead. This simple arrival time analogy perfectly mirrors how if, elif, and else statements work in code. We set up these conditions, and based on whether they're true or false, our program determines the exact action it needs to take. It's essentially a flowchart for automated decision-making.
Now, how we handle repetition is absolutely vital for automation. Let's say there's a guy named Jake who wants to print his name 10 times. Manually typing that out is super tedious, right? Well, loops do that heavy lifting for us. We've got two main types here. A while loop basically says, hey, keep repeating this block of code while a certain condition remains true. That is perfect for when you don't know exactly how many iterations you're going to need. Contrast that with a for loop, which iterates through a known sequence one by one. It's a lot like tackling your to-do list, checking off items item by item.
That brings us to Section 3, Functions, Modules, and Packages.
Let's start with functions. You can think of a function exactly like a baking recipe. Instead of measuring out your ingredients from scratch every single time you want to bake cookies, you just follow the recipe you already made. In programming, you use the def keyword to create a function, which is really just a reusable block of code that performs a specific task. Doing this saves a massive amount of time, it keeps your code nice and clean, and honestly, it helps you avoid making silly, repetitive mistakes.
This brings us to the Redford School analogy, which perfectly explains modules and packages. Imagine a school management system that starts out as one single huge, messy file. It is a total nightmare to maintain. So instead, you break that code down into specific modules. Things like student management, teacher management, grading. These modules are just individual Python files. Then, as your system grows even further, you group those related modules into overarching packages, which are basically just folders. This whole structure keeps everything logical, scalable, and super easy to find as your AI projects start to expand.
All right, Section 4, Writing Clean Pythonic Code.
When you're writing in Python, naming is literally everything. A function called cal with single-letter variables like a and b is incredibly vague. If you try to look at that 2 weeks later, you're going to have absolutely no idea what it does. Compare that to calculate_area width, height.
Here, we're using highly descriptive snake case naming. It makes the code's purpose instantly understandable to anyone who reads it.
And this is exactly why the source emphasizes that the PEP 8 style guidelines help us write cleaner, more Pythonic, and AI development-friendly code. This also means you should be properly using documentation strings, or doc strings, to explain what a function does right inside the code blocks themselves. It means using a consistent four-space indentation and, this is a big one, avoiding hard-coded variables by defining them as reusable constants up at the top of your scripts. Trust me, these practices are going to keep your AI foundation professional and rock solid.
Finally, we arrive at Section 5, Powering AI with NumPy. NumPy is what really unlocks massive processing power for us. At its heart is the n-dimensional array, or ND array. Now, unlike pure Python lists, NumPy allows for vectorized operations. That means you can do complex math across entire arrays of data almost instantly, without having to write a single, slow loop. It also comes packed with advanced mathematical tools, like linear algebra routines and a highly reliable random sampling module. And both of those, they are absolutely critical for running machine learning algorithms.
Broadcasting is arguably one of NumPy's most mind-bending features. Imagine adding a single scalar number to an entire massive matrix. Instead of throwing an error, NumPy automatically stretches that number's dimensions behind the scenes to magically match the matrix, calculating the whole result effortlessly. It saves a ton of code, runs lightning fast, and is just an incredibly efficient way to handle massive data sets in machine learning.
So there you have it. You now have the ultimate technical stack. We've gone from basic syntax and conditional logic all the way to clean architectural organization and the sheer mathematical muscle of NumPy. This Python foundation is your launchpad for interacting with cutting-edge large language models and eventually building your own autonomous agents. The only question left is, what intelligent system are you going to build first?